Today we're going to learn how to determine the molecular mass, or technically molar mass, of an unknown by colligative properties. So we've done this before, this meaning determining the molar mass of an unknown substance. This was used for gases, determining the molar mass of an unknown gas. We use, ideal gas law to do so. But this is a different approach. Same end result, though, we're determining molar mass. So let's take a look at this problem. There's one in your book, too, on page 532, if you need another example to take a look at. But I'm going to walk you through this one, and then I'll have you do a couple on your own. So it says calculate the molar mass, which is in grams per mole, or molecular mass, which is in AMU, of a non-ionic solute, so non-ionizing solute. Solution contains 8.02 grams of the solutes. Again, we don't know what that solute is. In 861 grams of water. And the freezing point of this solution is negative 0.430 degrees Celsius. So let's do this. Let's go to the very end. So in the very end of the process, we are going to determine the molar mass. We're going to calculate the molar mass. How do we determine the molar mass of an unknown substance? Well, if you recall, we take the mass of the substance, which I'm pretty sure is given to us, and divided by the moles, which we do not know. Okay, let's go to the very beginning. So we are given the freezing point of the solution. Anytime you are given the freezing point of a solution or asked to determine the freezing point of a solution, we're going to use the formula for freezing point depression. So we're given the freezing point, so we can use that to determine the change in freezing point. We know the Kf of the solvent, that is a constant. And so we can use both of those to calculate molality. So what's the link? We need moles here to calculate molar mass. Here we're going to calculate molality. How do we go from molality of the solution to moles of the solute? Well, the link between the two is actually the formula for molality. So start here, freezing points depression equation to get molality. We're going to plug that number in here. I'm pretty sure we know the mass of the solvent, though it's in grams, but we'll convert that to kilograms. So we'll know the molality once we calculate it. We're given the mass of the solvent in kilograms, which we can use then to find moles. And voila, we plug in moles there underneath the mass of the solute, and we can get molar mass. So let's go ahead and set this up. I'm going to clear the page and start over. So let's start with our formula for freezing point depression. So again, we're going to, though, calculate molality using that formula. So rearrange to solve for M. We get delta TF over KB. Now we have a freezing point of negative 0.430 degrees Celsius. So remember to calculate that, we take the freezing point of the solvent by itself, which is 0.000 degrees Celsius, minus our delta T, and that gives us the freezing point of the solution, which in this case is negative, whoops, let's back that up, negative 0.430 degrees Celsius. So what is our delta TF? Our delta TF is 0.430 degrees Celsius. So just wanted to show you how to do that. All right, so 0.430 degrees Celsius over the Kf of water, which is 1.853 degrees Celsius per molal. And again, you could do this all in one shot if you wanted to. I don't recommend this at this time. So why don't you pause the video and calculate the molality of the solution. So you should get 0.232 molal. And then what do we say? What's our second step? So once we know the molality of the solution, think about what else we know. We know the mass of the solvent. Be careful. We have two masses here. Only one of those is the mass of the solvent. One we're going to use at the very end, and one we're going to use right now. The one we're going to use right now is this. So rearrange the formula for molality to find moles. So we're going to take the molality of the solution, multiply it by the mass of the solvents in kilograms, and that'll give us moles of solutes. Go ahead and pause the video, see what you get. All right, should end up with 0.200 moles of solutes. Our last step is to calculate molar mass. We're going to take the grams, I'm going to do this down here, separate step, grams of the solutes given to us in the problem, divided by the moles of the solutes, which we calculated, and that'll give us our molar mass. Pause and see what you get. And we should end up with 40.1 grams per mole if it asks for molar mass. If it asks for molecular mass, technically we want to give the units in AMU, so that would be 40.1 AMU. All right, let's take a look at another example. Calculate the molar mass of a non-ionizing solute. Solution contains 64.3 grams of this solute and 390 grams of water. And the boiling point this time of the solution is 100.680 degrees Celsius. All right, so go ahead and pause the video and set this up. Calculate molar mass. So this time I did 100.680 minus 100 degrees Celsius. So subtract the normal boiling point of the solvent from your boiling point of solution to get the delta TB. Use that along with KB to find the molality. We got 1.32 mol out. I don't know why I have parentheses around this. I want to do it in separate steps instead of mixing everything together. Take the molality along with the mass of the solvents and use that to find moles of solute. Take grams of solutes, which is given to you in the problem, divided by moles of solute, and that will give you molar mass, 125 grams per mole. One more. This time we have 20.8 grams of some unknown solute and 128 grams of acetic acid. The freezing point of the solution is 13.5 degrees Celsius. Calculate the molar mass of this unknown. Go ahead and pause the video and do so now. All right, so notice this time our delta T has 2 sig figs. So we do take the freezing point of the solvent by itself, acetic acid, which is 16.66 degrees Celsius, minus the 13.5. Because this has only one digit after the decimal, the difference will have one digit after the decimal. We get 3.2. And then when we calculate molality, that also has 2 sig figs. And from there on out, everything else has 2 sig figs. So if you did this all in one shot and rounded at the very end, may get a little bit different results. So you get 208 grams per mole, but we want 2 sig figs, so we're going to round that up to 210 without the decimal. That's 2 sig figs, so about 210 grams per mole. All right, that concludes this lesson. Thanks for watching.